Just at the beginning, I would like to make a few remarks. So you know, meanwhile, that originally we wanted to have this seminars on Tuesday, our seminars on Tuesdays. We were asked by the INI to shift that because there is another program running that also have chosen the Tuesday for their seminars, and they didn't like the overlap. So then we moved everything to Monday, but this was only decided last week very late. So it was very difficult to find a speaker or speakers for Monday or Tuesday, exceptionally, because today we meet exceptionally on a Tuesday. And so we were under some pressure to find speakers, and we thought this is impossible. And in order not to lose another week because of this pandemic, because we are not at the place but have to do everything online, we decided, we means the 5 organizers, that we just start to get started this week. Otherwise we would have lost another week. And then starting from next week, it will be sort of regular. And as I said before in the email of Vasily, you should send your request to give the talk, including title and abstract, to him, and then we'll try to accommodate all these talks. Okay, this is just a preliminary remark, and now we are very happy to announce the first speaker today. So it's Eulalia Nualart. I do not know. How do you pronounce it, Eulalia? Can you teach me? Lipschitz, okay. And so her title is Non-Existence of Solutions to Fractional Stochastic Heat Equations. Please go ahead.
Okay, thank you very much and welcome everybody. So this is a semester on fractional differential equations, and here I'm interested in the stochastic part and in FDEs, so for the fractional stochastic heat equation, okay? And I'm interested in results of blow-up of solutions, okay? This is a joint work with Mohammud Foondun from the Universitat of Strathclyde. So let me start from the beginning, okay? What we call the Osgood condition for ODEs, that I'm sure most of you will know, is very simple. So you consider an ODE where the drift is assumed to be non-negative, locally Lipschitz to get the existence of local solution, and non-decreasing, okay? So this equation admits a unique solution up to its blow-up time. And it's easy to see, using the fact that B is non-decreasing, that the blow-up time, which is the sup of that xt is finite, is the integral of 1 divided by the drift, and the integral goes from the initial point to infinity, okay? So in general, we say that the solution blows up in finite time if t is finite, okay? So this is ODE, okay, ODE result. Okay, so this was extended by Leon and Villa in 2011 for ODEs that has so a drift plus a continuous function, right? And in this case, the finiteness of this integral is called the Osgood condition, okay? And they show that if, so assumption 1 is the assumption that I will have during all the talk, which is that B is non-decreasing and locally Lipschitz and non-negative, okay? And assumption 2 is the assumption that we need on the continuous function G. And the assumption is that G is continuous, okay? And it takes the solution to infinity. So the limb sup when t goes to infinity of the infimum over h of g t plus h is infinity. Okay, so this says, under this assumption, we have that the solution to this differential equation blows up in finite time, even only if the Osgood condition, so the same condition for the ODE without G holds. Okay, and the proof is the following. The proof, the sketch of the proof is the following. So first of all, so recall that xt equals to this. First of all, assume that the equation blows up in finite time. Okay, so that G is finite. Then G is continuous, so the supremum over a finite interval is bounded. Okay, so we can bound the equation and we can use a comparison principle with this ODE for which we know the blow up time. So if T is finite, xt will blow up in finite time, so will yt. Okay, and yt is an ODE with drift B, so B satisfies the Osgood condition for some A. Right? Remember that the Osgood condition is that for some A. So this is the one implication. The other is a bit more tricky, is where we use the condition on G, and it says the following: suppose that the solution does not blow up in finite time. Take Tn a sequence that converges to infinity, and then the idea is to lower bound xt plus Tn by the integral of the drift on S plus Tn plus the infimum of the continuous function. So this means that now we are going to compare xt plus Tn and the solution to this differential equation. In particular, this is bigger than 1 because x does not blow up on finite time. And now we use assumption 2 that says that there is a sequence that goes to infinity that pushes this to infinity. So this contradicts the Osgood condition. This integral cannot be finite. Okay, so this is the other implication. Let's put some stochastic now. Let's consider the bifractional Brownian motion. The bifractional Brownian motion was introduced by Udre and Villa in 2003. It's a centered Gaussian process with these covariance. It's a generalization of fractional Brownian motion. So when k equals 1, we get fractional Brownian motion. When k is between 0 and 1, we have a more general covariance at fractional Brownian motion. Arcones in 95, so following Arcones 95, we can easily show law of iterated logarithm for this bifractional Brownian motion with respect to this function. And this is going to be crucial for what is going to be true next. So what Leon Villa extended their result, adding to the equation a bifractional Brownian motion. And they show that the solution of this stochastic differential equation blows up in finite time almost surely, even only if the Osgood condition holds. And this is because we are able to show, using the law of iterated logarithm, that that almost surely there exists a sequence that goes to infinity that pushes the fractional Brownian motion to infinity. Okay, so as soon as we have this, we can use the other result for a fixed omega, and then we get the result almost surely. Okay. So, well, I sketched the proof, but I will pass it since I don't have much time. But the idea is to prove this lemma, okay? And to prove this lemma, one uses the log of iterated logarithm, and one uses also the continuity properties of the fractional Brownian motion. Okay? And now I'm interested to extend it to SPDs. Okay, so I consider first the stochastic heat equation with a drift B and space-time white noise, and in 0, 1, with initial condition and non-negative and continuous function. Okay, so B, as before, is assumed to be locally Lipschitz, and since we are in 0, 1, we know that there exists a unique local random field solution that writes like this. So P is the Dirichlet heat kernel. Okay, so there exists a unique local random field solution up to the stopping time, the supremum of U. And the idea is to extend the results. So what is known about the existence of solutions for this equation? So let me first recall the known results. There is a theorem by Bonder and Groisman in 2009 that says that if P is not negative, locally Lipschitz, and convex, then if the Osgood condition holds, then the solution blows up in finite time. Okay? And there is a more recent theorem that was the starting point of our work by Dalan, Kosnevishin, and Zhang that says that if B is locally Lipschitz and is big O of x log of x as x goes to infinity, then there exists a global solution. So observe that if B is comparable to x log of x power delta, then the Osgood condition holds even only if delta is less than 1. So what Dalan, Kosnevishin, Zhang shows is that the Osgood condition is optimal. Okay. Okay, so based on these results, our result for this equation was to first prove the converse of Bonder and Groisman. So Bonder and Groisman showed that Osgood condition implies solution blows up in finite time. So the first thing that we did, our first theorem is that assuming, so we didn't need any convexity, we just need non-decreasing. If the solution blows up in finite time with positive probability, then P satisfies the Osgood condition. Okay, so this is our first result. Okay, observe that Bonder and Groisman shows that if B is of a power, then there is no global solution, no matter how small the initial condition is. Okay, for PDEs, this is different. One can construct non-trivial global solutions by taking sufficiently small initial conditions. Okay, so let me just give you the idea of the proof, which is the necessity of the Osgood condition. And it's very similar as what Leon Villa did. Okay, the idea is to assume that there is a positive probability that that the solution blows up in finite time, fix this omega. Okay, and then we can bound this. By a constant almost surely. Okay, and then we get an upper bound, and when we can use again the comparison principle to show that the Osgood condition holds. Okay, so the proof is very similar because we are in a bounded interval in the Dirichlet case. Okay, so we know that the supremum is going to be bounded. Okay. Right, and now the idea is to extend all these to the fractional Laplacian. Okay, so now instead of a usual Laplacian, we put here a fractional Laplacian, okay, which is the generator of a symmetric alpha-stable process, killed upon exiting the ball. So it's a fractional Laplacian on a finite domain, on a bounded domain, okay, and we put homogeneous Dirichlet boundary conditions to be 0 to simplify, okay. And the noise is white in time, and since we are in multiple dimensions in RD, we need to put a special correlation whose Fourier transform is a tempered measure satisfying this. This is to get continuity of the solution, okay, so hold the continuity of the path, okay. By the results of Saint-Soulé and Serrat, this condition implies hold the continuity of the solution, okay. So now the question is, does Osgood condition gives necessary and sufficient conditions? And the answer is yes. Okay. So this is our theorem. Again, B is locally Lipschitz. So again, we are in a finite domain. So there is a unique local random fit solution up to the explosion time. And P alpha is the Dirichlet fractional heat kernel on the ball. Okay. So again, assume that B is not decreasing. Then our result says that if P satisfies the Osgood condition and is convex, so here we are extending the result by Bonder and Groisman, the solution blows up in finite time almost surely. So this is one implication. And the other implication says if the solution blows up in finite time with positive probability, then B satisfies the Osgood condition. So we get necessary and sufficient conditions for the Osgood condition, for the fractional heat equation in terms of the Osgood condition. Okay. So let me quickly sketch the proof. The sufficiency follows similarly as Bonder and Groisman. Okay, the idea is to use the spectral decomposition of the fractional heat kernel, okay, and then multiply U by the first eigenvalue, okay, by the first eigenvector, okay, which we know it's particle, okay, and then one can easily show that when you multiply the solution by the first, and you use the random field solution, you get this integral, okay. And then the idea is to use the fact that B is convex and Jensen's inequality. And this shows that our solution is comparable to this stochastic differential equation driven by a Brownian motion with variance given by the correlation function. And then use a comparison, use Feller's test for explosions and a comparison principle to show that, that the solution will blow up. Okay. So this is the sufficiency of Osgood condition. If the Osgood condition holds, the solution will blow up almost short. Okay, and the other half is similar as before, so I didn't include it. And now the question, so here, some extensions. Does this extend to multiplicative noise? Okay. Only for the moment, we are only able to show that if the solution blows up in finite time with positive probability, then B satisfies the Osgood condition as soon as B is bounded. Okay. So the necessity of the Osgood condition. However, this argument by Bonder and Groisman does not seem to extend when there is a sigma, when there is a general multiplicative noise. So this is still an open problem. Okay. Right, and the last extension is to consider the stochastic equation in R. For this equation, much less is known about blow up. Okay, so now I consider, so let's start with a non-fractional, the usual one. Okay, and in R, and then we ask if the Osgood condition is a necessary and sufficient condition. Okay, so here, this equation is a bit complicated because we cannot use the same argument to construct local solutions. So actually, existence of local solutions is an open problem in general. Okay, there are some partial results, but we cannot. The idea of to construct local solutions, no, in 0, 1 in the Dirichlet case, is to truncate the drift. Okay, and then construct the solution with the truncated drift. But here in R, we cannot do this argument. Okay, so here our theorem assumes a priori that there is a local solution, and the theorem is the following: is that B is a sufficient condition. So if B satisfies the Osgood condition, then almost surely there is no global solution. So we were able to show the necessary condition in R. Okay. So this shows that if B is a power, then there is no global solution, meaning that there is no Fujita exponent in the stochastic setting. So again, if we compare with the deterministic setting, we see that when the deterministic setting, when eta is bigger than 2 divided by D, one can construct non-trivial global solution for sufficiently small initial condition. For the stochastic setting, no matter what eta is, there is no global solution. Okay, that this is what our theorem shows. Okay, and let me give you the proof because the proof is interesting. So, so the idea of the proof is to use the fact that if you consider the solution when B is 0, when there is no drift, so the stochastic term, this, when X is fixed, this is a bifractional Brownian motion with parameters 1/2. H equals 1/2 and K equals 1/2. Okay, this was proved by Lay and Nualart in 2009. Okay, so using this and some continuity properties of the solution, we are able to show the condition of Leon and Villa. Okay, that there exists a sequence that pushes the stochastic part to infinity, and this is how we get the blow up. Okay, so this is the idea. Okay, so again, I will skip the details, but the idea is to use the same argument as Leon and Villa plus some continuity lemmas, Garcia's lemma, a little improvement on Garcia's lemma that we obtained with the Lang and Groisman that allows us to show the result for any x, right? Because here we need to show that the result is true for the infimum of x, okay? Because here is for fixed x is a bifractional Brownian motion, so one cannot directly apply the law of iterative logarithm of bifractional Brownian motion. One needs to control the dependence on x, okay? And finally, let me show you how these extend to the fractional Laplacian. Okay, so now consider the fractional Laplacian and the stochastic heat equation on RD, in all RD. Again, local solutions are not known. The existence of local solutions in general is an open problem when B is locally Lipschitz. There are partial results, but not a general result. Okay, again, well, here we are going to assume that the spatial correlation of the noise in space is a Riesz kernel, so a power. And we were able to show that if B satisfies the Osgood condition, then almost sure there is no global solution. Okay, and what is the idea of the proof? The idea of the proof is very similar to the case with non-fractional. The idea is to consider the stochastic part of the mild formulation, which is the integral of the fractional heat kernel with respect to this noise, which is white in time and fraction and Riesz kernel in space. And then we observe, if you compute the covariance of this Gaussian process when x is fixed, so if you consider this Gaussian process, this is also a bifractional Brownian motion in the fractional phase. The parameters are h equal to alpha minus beta divided by 2 and 1 divided alpha, where alpha is the fractional Laplacian. Okay, so the solution to the solution to the linear fractional equation when x is fixed is a bifractional Brownian motion. Okay, so one can imitate what we did before and show that this infimum, that this Gaussian term will push the solution to infinity as well. Okay? And this allows us to prove the theorem of the necessity of the Osgood condition. Okay? So this is the key step of the proof, okay? To show this fact. So that's it. I just finished with some references. So this is the paper by Leon and Villa, the paper by Bonder and Groisman. This is the paper by Dalan, Kosnevich, and Duchenne that was the starting point of our work. And this is the reference of our paper that was published last year in Berlin. So thank you very much for your attention.
Yeah, thank you very much for the very nice talk. Are there any questions?
I think I may ask some.
Yeah, please, Vasily.
So, Eulalia, very nice result, but of course, question is very natural somehow arises from our program. What if you put this instead of the normal temporal derivative, if you put fractional temporal derivative?
Here.
What happens then?
Here, right?
Yes.
Good question. Let me think. So there are results on that, on the existence and unique. So there is a mild formulation for that as well, which I think Mohammud Foondun has worked on that, my co-author. So you can get a mild formulation as well. So, okay, let me go to the mild formulation. So that's a good question. There is a mild formulation as well. And so it could be, so it should be studied. Yeah, I think it's a good way. It could be done, but
yes,
one would
I think so. I think it's very natural extension. Yeah, will be very interesting.
Yeah, it could be extended. My guess is that it could be extended. Yeah.
Okay, are there any other questions? Could you please use the hand raising option under reactions when you go down? Then I will not overlook that you want that you raised your hand. But there was a raised hand before. Boris, right, go ahead.
Hi, Michael. Hi, Eulalia. Nice
Hi.
talk. At some point, you were looking at the heat equation, or the fractional heat equation on a unit ball. Did I understand this correctly?
Yes. Yeah, sure.
And you were claiming that the fractional Dirichlet Laplacian is the generator of the
So here is a fractional Laplacian.
stable process killed upon exiting the ball.
Yeah.
I don't think that's quite right.
So you mean that here I put the generator of a symmetrical first-order process, and this is not exactly the fractional Laplacian on the ball?
That is not exactly. That is not a Dirichlet Laplacian. It's a truncated.
Okay. Yes.
kernel.
Okay. I agree.
So with that, your representation by the spectral sum is correct for the Dirichlet Laplacian, but not for the generator of the alpha stable. So this slide is correct, but it does not correspond.
Okay, I see. It's
to the stochastic process that you're trying to model, or that you're claiming to model.
Okay. So you said that here I should put the
So Alice is certainly a generator of a nice stochastic semigroup it's actually of a subordinated killed process, but not of the alpha stable process that's being killed. There's a slight difference. So also the solutions, then the behavior at the boundary is quite different between the two processes.
So analytically, it is completely correct. It is just the probabilistic interpretation that is.
that I should be
Exactly, yes.
when in the definition of L. Okay, thanks. Yeah.
Great. Okay, are there any other questions? So if I overlook somebody, then just start speaking. But then there seems to be no more questions. I just have one question. It is about the, just a moment, Rico. Oh no, just go ahead. Rico, you go ahead, it's fine.
Okay, thank you. I just want to add a comment on the question raised by Vasily on the time fractional case. So concerning this Osgood condition, there is a similar result in the time fractional case. Let's say just in the purely time-dependent case, so you can prove a similar blow-up result. And this can be extended to the PDE case on bounded domains using this eigenfunction method presented in this talk. Yeah, so this is known, and this is it's also possible to extend this to more general kernels where you have subdiffusion. Yeah, so this exists already, but this is for the sufficiency part. Yeah, so I don't know about necessity. This could be interesting. And I don't know much about the full space case, but for bounded domains, there exists already results.
Okay. So
and I can give you.
If you can give the references by the chat, it could be nice.
Yeah.
Or
Yeah. Okay.
By email. Thank you. I was not aware of that.
Okay. So next question is by Zhislav.
My first question was actually answered by Boris, but I have a second question similar to Vasily. So, has anybody studied similar problems for hyperbolic equations, like so say wave equations?
That's a good question. So we have actually we have extended all these to the wave. Yeah.
And the reference?
And so I didn't include it here because the talk was so short that I didn't want to talk about the wave, because in the wave there is anything fractional, and since here we are in an audience of fractional, that's why I didn't talk about it. But yeah, we have considered the one-dimensional stochastic wave equation And for the three different cases, all are D or bounded domain or bounded interval in this case. And we have a recent paper which is in revision for a journal. And yeah, so it's in archive. So you can.
So your paper with Foondun?
With the same co-author, with Mohammud Foondun. So here.
No.
If you look at in my website, you have the paper as well.
Yeah, okay, thank you.
Or in archives. Yeah, so the natural question is to extend all this to the wave. And it's an interesting, it's an interesting phenomena, because then there is no Osgood condition. The condition is a bit different. So the condition is involves a different Osgood condition that it's known for PDEs, but it was not known for SPDs. So we have found the condition for SPDs. Yeah.
Okay, Gisela.
No, thank you very much.
Thanks.
Rico, this is your old hand up, right? Or is it a new hand up?
Okay, so should I raise my hand?
Yeah, Gisela.
Lower my hand, yes.
But Rico, is it a new hand up in your case?
No, it's not.
Lower hand,
It's
okay.
the old one. Okay, no problem.
Sorry.
Yeah, okay.
Okay, so yes, I just have a question of understanding in the one-dimensional case. When you Eulalia, when you said the one-dimensional case, you always meant white noise in that case, in contrast to the higher dimensional case, right?
Yes. Yeah.
Okay. Just I wanted to make sure.
One-dimensional, I mean that X is in an interval, and then it's a space-time white noise. Yeah.
Okay.
And for the wave, so far we have only been able to do the one-dimensional case. Here we have covered all the cases.
Okay, very good.
Even if there are open problems still, no? But we have covered all the possible cases except the fractional derivative yet,
Right.
which will be the next extension.
Okay, then I would suggest to thank the speaker again.
Thank you. And I will stop sharing.
And we can pass over to the next talk. I just want to